Assalamu alaikum. So basically lab 2 has been uploaded, and before you guys proceed on lab 2, I'm just keeping this tutorial to let you know about some basic functions per se and basic commands in Python that you might need to know how to implement, and it's going to help you out in the lab as well. So just so that you're not entirely blindsided, so you have an idea of what's going on. First of all, you already would be familiar in how to make matrices. Let's say I make a matrix np.array. I'm going to make a 2D array. Let's make a 2 by 2 array. 1, 2. Yeah. This is a 2 by 2 array. We'll print it out as well. And what we want to do is find its inverse. So as you can see, these commands are given to you in the start of the lab as well. You'll be importing them. The two commands that are important or basically numpy. You know how you've already imported numpy. So what we're going to do is we're going to use the linear algebra tools in numpy to take inverse. How do you take inverse? Let's say b is going to be the inverse of a. np dot linalg stands for linear algebra dot inv inv. I just give it the argument, which is in a 2D array, and it is going to take an inverse, and let's print that out as well. Let's see how. Okay, see, this was a 2 by 2 matrix 1, 2, 3, 4. Now b is its inverse, minus 2, 1, 1.5 minus 0.5. This is how you take an inverse. Now, inverse exists for square matrices. That means 2 by 2, 3 by 3, 4 by 4. Later on, you'll study, maybe this week as well, that if you do not have a square matrix, or maybe the third week, you have a rectangular matrix, a tall matrix or a fat matrix, you'll come to know about these things, then you can't exactly take an inverse. For that, you need something called a pseudo inverse. Again, I'm just going ahead to let you know about a command. You'll learn this in theory, and you don't need this right now, but it's good to know. Just like inverse, the only difference is p inverse. It's called pseudo inverse. So when you get to that, just keep that in mind. Now this is how you take an inverse. Other things that you might need is how to do eigenvalue decomposition, right? So for eigenvalue decomposition, C is equal to np dot, again the same commands, linear algebra dot eig, right? So this, when you do eigenvalue decomposition, you will learn in theory as well, you get eigenvectors and eigenvalues of this matrix. Both of them are going to be stored in C. So the first, I'll show you how to print it. And first eigenvalues are stored. They're stored on the first index of C. C will be an array. So the first element in C would be the eigenvalues, and the second element in C will be the eigenvectors. You might have the order reversed, but let's see. Yeah. Now you see the eigenvalues are minus 0.372 blah blah and 5.372 to 8132. These are the eigenvalues, and the corresponding eigenvectors, they're represented in a matrix. This is the matrix of eigenvectors. You will see when you do EVD in class. At eigenvalue decomposition, there is one matrix in which the columns are eigenvectors, and there's a matrix in which the diagonals are the eigenvalues. Now, one eigenvector is minus 0.82456484 and 0.565767746. This is one column. This is one eigenvector. The second eigenvector is the second column. So this is how you can extract eigenvectors and eigenvalues of a matrix by this command right here. Okay. Another thing that another manipulation that you might need in EVD or SVD in either case is if you have values, for example, if you have eigenvalues and you want to construct a matrix on which the eigenvalues are on its diagonal. Like we have a matrix and the diagonal elements are the eigenvalues and all other elements are 0. For example, if you have two eigenvalues, you'll have a 2 by 2 matrix in which one value will be at one location, the other will be on the other location on the diagonal. You can do that simply by C0 has the eigenvalues now. So we make a function called np.diag. This will make D a diagonal matrix with the values of C0. Let's print that out to see. Yeah. So these were the eigenvalues. And now we have a matrix, which is a 2 by 2 matrix with these values at the diagonal. Now this command, if I'm not wrong, it works both ways. Now D is a 2 by 2 matrix, right? So if I apply the command again, but this time I'm not inputting a linear array, I'm not making a diagonal out of an array. I want to make an array out of a diagonal. That means I want to go the other way around. If I input a matrix, this command should extract the diagonal elements of the matrix and place them on an array. I hope you understand. It's going to extract the diagonal elements and just going to place them in the array. So this should give us an array. See, back here again. First we had an array. If we apply the command on an array, it gives us a matrix where the values are placed on the diagonal. If we give it a matrix, it's going to extract the diagonal values and place them in an array. So this command np.diag goes both ways. Right. So this was just to demonstrate that fact. And this was just for eigenvalue decomposition. Now, another thing that we can do is singular value decomposition, SVD. So we're going to input A. We want to do a singular value decomposition of A. Now, I'll show you what this is. First element, second element. I'll explain this in a second. Right, singular value decomposition, just like eigenvalue decomposition, EVD, it makes eigenvectors and eigenvalues. But singular value decomposition, as you'll study in theory, is that there's one matrix called the sigma matrix. It has singular values. Like eigenvector decomposition, EVD has eigenvalues, SVD has singular values. And that is the second element here. And then there is the left singular, just like the EVD decomposition had eigenvectors, SVD has a little variant of that. It has singular vectors, but there are two kinds. There's left singular vectors called U, and there is right singular vectors called V. Now, what this decomposition returns is three things. It returns left singular vector, which is u, which is the first element. I will check the order of the element as well. It returns the singular values, and it returns v transpose. It doesn't return v. You just have to keep this in mind. It returns v transpose. If you want to extract v, you have to take a transpose of this. Let's run it. Yeah, see, you first got a 2 by 2 matrix, which is u. Then you got two singular values, and then you got 2 by 2 matrix, which is v. Now the thing about SVD is, which you will also learn in theory, is you can do that not for just square matrices. For example, if we have a 2 by 3 matrix, so if we have this matrix, oh sorry, see this error came here because inverse doesn't work. Like we said, inverse only works for uh, square matrices. But although you don't need this, but if I just were to show something called pseudo inverse, which you will learn, it's going to function because you can calculate pseudo inverses of rectangular matrices. Now, you got a U, which is a 2 by 2 matrix. You got two singular values, and now V transpose is a 3 by 3 matrix. This is how SVD decomposition takes place. U and V are not the same. They're not like EVD, in which you have just eigenvectors and eigenvalues. These are singular values. This is a left singular matrix. This is a right singular matrix. And again, if you want to place these singular values on a diagonal, you use the np.diag command. That's mostly what SVD is. Right. Now, let's say we create. Yeah, let's say we create a three-dimensional array. This is a 2 by 3. We can make a 3 by 3, and okay, let's make 3 by 3 array to show you one thing. Now we have a 3 by 3 array. Now what I want to do is I want to take an average across the first dimension. For example, you have one dimension here, you one dimension here. 3 by 3, right? 1, 2, 3, 1, 2, 3, 1, 2, 3. You want to average out the rows. For example, you want to average these out. These. So you want to get a 1 by 3. You want to get a 1 by 3 in which or you take the average of this, average of this, average of this. So you want to convert 2D into a 1D. There's this command that you would require to convert a 3D image into a 2D image in the lab, as you'll see. So basically you want to reduce one dimension. What you do is you take the mean across that dimension, right? And how do you do that? I will just do np.mean. I want to take the mean of A across which dimension? Across the 0th dimension or the last dimension, which would be 2 in this case. This means that I'm if we have 3 dimension, this will take the mean across the 3rd dimension, and this is going to return B. Now see here, this gave us an average. Now it's a 1D array, it's a 1 by 3 array. So it gave us an average. 7, 10, 11, 11 by 3. So we just have to check across which dimension you took the average, the rows or the columns. That you just need to figure out, but you can specify the dimension here if it's which dimension you want to take the average across. Now you know how to take an inverse, pseudo inverse, which will help later on. You know how to do eigenvalue decomposition. You know how to take diagonals and convert diagonals, and you also know how to do single value decomposition, take mean. Now, if you have a 3 by 3 matrix, for example, let me just clear it up. We have sorry, we'll save it. You have a 3 by 3 matrix, right? Now, let's say I want to take a 2 by 2 block. I want 1, 2, 3, and 4. I want to extract just 1, 2, 3, and 4. I want to extract a 2 by 2 block of A. We already know how to do array indexing, but this, just to reiterate, this is how you index a 2D array, right? If I were to index, let's say 0, 0. Oh, sorry. Oh, got you. We just got this element, right? Now I want to extract a 2 by 2 matrix, right? So what I want to do is, now if you want to extract a 2 by 2 block, what you do is just take all the elements to the second element, take all the elements to the second element. This is what you do to extract a 2 by 2 block. See, A was 1, 2, 5, 3, 4, 6, 7, 9. Now it's 1, 2, 3, 4. Similarly, if I want to extract a 3 by 3, this is just the entire thing. Now if I want to just, if I do this, this is going to take just the first row and all the elements in the column. So this is how you can manipulate arrays and matrices, which you should be comfortable with. And the other thing is just multiplying matrices, which you would have had experience in the last lab, how to multiply two matrices. It's np dot, and you multiply A and B. Yeah. So that should be enough to give you an idea. And I already told you about the imread command. It's in the manual. If you want to read an image, I don't have an image right now. Just do imread, imread, and for example, just write the name along with the extension. And this file should be in the same directory that your .py file is in. And it's going to read, and it's going to store the image as a matrix in C. And then you can do further manipulations in C. So yeah, that is how you read an image. And okay, one more thing. For example, we have an array. This might help you. You might need it, you might not need it, but just generally now, since we are on this topic. Right, you have an array. There's something called cumulative sum. This is the function for cumulative sum. I will just show you what it does. Right, so this is our original array 1, 2, 3, 4, 5, 6, 7. Cumulative sum takes keeps on telling you the total while adding all the previous values. For example, 1. And the next value is the sum of, it just adds the next value to the previous all values. It adds 2, so you have 3. Next value, it adds 3 to the already previous 3, which is 6. And next value, it adds 4. So basically you're accumulating values. 10, and then you add 5, 15, then you add 6, 21, then you add 7, 20. You're basically accumulating values one by one. It's just a neat function. You might do this task through for loops or some extensive method, but this is just a neat function if you're already not familiar with it. Right. This should cover everything and more that you're going to need for your lab. So this is just an overview of some functions and some commands that might help you to make sure you get through the lab more easily and you actually understand what you're doing and you don't get stuck in the syntax, but you actually focus on the content, right? So I hope it helped. Good luck for your lab. Thank you.